Hi, everybody. All right. I hope you're all ready to get back into related rates because we've got some fun word problems today. And then we're going to talk about differentials. So here we are, starting off on example 3. Susan is in her car leading a group of other drivers to a restaurant. She's in the blue car. She's just completed a right turn at an intersection and is accelerating away. At the moment that she is 40 feet from the intersection and heading north at 25 feet per second, the second car in the convoy is still 40 feet away from the intersection and is approaching at 15 feet per second. How fast is the as the crow flies distance between Susan and the second car increasing at that particular moment? So we're faced with this related rates problem. Some of the major things that we need to sift through is what information have we been given? What are we being asked to find? How could we put all of this into some helpful diagram, which is thankfully kind of already done for us in this problem. We're at an intersection. That means that Susan has made, yes, a right turn at a 90-degree angle, and we're looking at a right triangle. We've been asked to find how fast is this as the crow flies distance between Susan and the second car increasing at the particular moment. And it's already labeled on the diagram there, but we're looking for dH dt because H in this context is the hypotenuse of that right triangle. And I guess, in order to solve this problem, what we really need is an equation that relates the sides of a right triangle. So Pythagorean theorem makes sense. We'd have x squared plus y squared equals h squared because, x is this distance, y is this distance, h is the hypotenuse. And in order to get the derivatives with respect to time in there, what we're going to do is take the derivative of everything with respect to time. And as we do it, we treat x, y, and h as functions of time. So we're going to use the chain rule. So 2x dx dt for that first part, 2y dy dt for the second part, and then 2h dH dt for the second. And look at this, we got a dH dt. So this is what we're being asked to find, and hopefully we're going to have enough information to solve for dH dt. I think we do. X and Y are both 40 feet. So I'm going to go ahead and just write, 2 times 40 in both places as 80. So 2 times 40 is 80. I'll leave dx dt there for now, so we're not super confused. We can handle the dt stuff in the next step. This one, the hypotenuse, h is not solved for right now, but if you're to use the Pythagorean theorem here, especially since we have an isosceles right triangle, the ratio between these side lengths is going to be 40 times the square root of 2. So this one I'm just going to write as 80 times the square root of 2 for the length of the hypotenuse, and dH dt is still hanging out. All right, and we have been given values for dx dt, dy dt. It's a little bit more tricky to parse those out from the paragraph, but on the diagram, I think they're labeled pretty nicely. So dx dt comes first. That one is negative 15 feet per second. Yeah. Because that side of the triangle is thinking as the yellow and red cars move towards the intersection. The other one, Susan, is driving away at 25 feet per second. And now we've got an equation where dH dt is the only unknown. Okay, thinking about the distributive property here, I think that 80 times negative 15 plus 80 times 25 would be the same as 80 times 10, which is 800. And then dividing both sides by 80 square root of 2, we would have 10 over the square root of 2 equals dH dt. And yeah, that's a fine answer. I mean, you could rewrite it if you, I don't know, it doesn't matter, but you could rewrite it as 5 times the square root of 2. I believe that that is approximately 7.07 feet per second. But yeah, that makes sense that the as the crow flies distance is increasing because Susan is driving away faster than the other cars are approaching. Cool. All right. Have any questions on that? Let's go ahead and take a look at the next one. All right. Sorry if this question's a little corny. Corn falling from the end of a conveyor belt at a rate of 10 cubic meters per minute, and it's forming a conical corn pile below. As the corn falls, the height of the pile is remaining equal to the diameter of the base. How fast are the height and radius of the pile changing at the moment when the pile is 4 meters high? All right, so let's again try to identify the important stuff that we've been given. This, this diagram's already, kind of labeled. We've got more information. It's not as fully featured as the last one. Okay, the first thing we have is this 10 cubic meters per minute. To me, that's a rate of change of volume. So I'm gonna write dV/dt there, just, as shorthand, but that's volume changing. We also have a relationship between the height of the pile and the diameter of the base. Okay, those two things are equal. Good to know. How fast are the height and radius of the pile changing? All right, well, this we could label as dH dt, how fast the height's changing. The radius changing would be dr dt. And at the moment when the pile is 4 meters high, so, okay, 4 is height. So, I don't know, we can just write h there. All right, so we've got some good things there. We need some kind of formula that relates the volume and height and radius of a cone. All right, so volume of a cone. Volume is equal to 1/3 times the relevant cylinder. So the cylinder would be pi r squared, which is the area of the base, times the height. Cool. All right, so we've got a good formula for volume. And now we need to get all the dt stuff in there. So we're going to take the derivative of everything with respect to t. Before we do that, now you could do it right now. You could take the derivative of everything with respect to t. And you would be treating r and h, the radius and the height, as functions of t. You could do it right now, and you would need to do a product rule between the r squared and the h that's happening there. But if we do a little bit more work on this equation before taking the derivative, then we might not even have to do the product rule, which could be great. In that second sentence, we have a relationship between the height and the diameter of the base. So what we have is the height is equal to the diameter of the base. The height is equal to 2 times the radius. And then we got to think about, can we use this to make a substitution here and, get rid of one of those variables? The answer is yes. And honestly, we could do it either way. We could put in 2r in for h, or we could put in 1/2 h in for r. Doesn't matter. You know what? I'm going to go a way that probably I wouldn't normally. I probably would just normally put in 2r for h and call it a day. But since we've got h here as, the height, let's change everything in terms of h and see how that goes. So, yeah, let's make the substitution, where this is the same thing as 1/2 h is equal to r. And so we go over here and we get 1/2 h squared times h. And then we've got 1/12 pi h cubed is an equation for the volume. No derivatives have been taken yet. We just got this into a one variable equation on the right hand side rather than a product rule. Nah. Okay, now let's do this back into taking a derivative with respect to t. So we get dv dt is equal to, well, we'd be using the power rule on h. So that 1/12 is going to turn into 1/4 because we're multiplying it by 3. Pi just comes along for the ride, and we've got h squared dh dt, because chain rule, we're treating h as a function of time. And now we've got enough information to solve for dh dt, I think, because dv dt is 10 cubic meters per minute. And the height is 4. And so, yeah, if we wanted to solve for dh dt, we've got 10 is equal to 4 pi times dh dt. And I don't know, 10 divided by 4 pi, whatever that is dh dt. I think I remember doing this, and it's roughly 0.8 or something like that. Meters per second. No, meters per minute, sorry. But yeah, that's a cool thing for the height. And I suppose we could do the same thing for the radius, since we're asked for dr dt. I guess one thing that you could just reason through this, and since the height is always 2 times the radius, you could just think, oh, I multiply that by 2 to get that. But how about we go back up to this equation and we actually take some derivatives with respect to time here. We'd have dh dt is equal to 2 times dr dt. And then, we could be confident that when we put in, well, all right, so let's just write the 10 divided by 4 pi, which is 5 divided by 2 pi. But anyways, we could divide both sides by 2, and we would get 5 divided by 4 pi is equal to dr dt. So dr dt is going to be a little bit slower. So about 0.4 meters per minute, probably. Cool. And there are 2 rates that we were asked to find. All right, moving on to the next one. Here we got a balloon, and why don't I make us a little bit of room just in case we need it. Get that linearization out of the way. All right. A spherical balloon is being filled with helium at a rate of 200 cubic centimeters per second. The moment when the radius is 20 centimeters, how fast is the surface area of the balloon increasing? Okay, so we have a dv dt. We've got, a rate of change of volume. We have a radius. Okay, that one's kind of boring. And we're being asked how fast the surface area is increasing. I would probably label that as maybe dA dt for area. Aha. All right. We've got a sphere. That's nice. We know the formula for the volume of a sphere. We know the formula for the surface area of a sphere too, but those are going to be 2 different equations. And I don't really know any equations that relate volume of a sphere to surface area of a sphere. Perhaps we could make one up. Maybe we'll try that. After maybe just considering the 2 equations separately. I know the 2 equations separately, things going to work. All right. So volume of a sphere would look like volume is equal to 4/3 pi r cubed. Surface area would just be 4 pi r squared. All right. So those have r's. We need to get them changing. So let's take derivatives with respect to time. dv dt is equal to 4 pi r squared dr dt, because we're treating our radius as a function of time. So that's a chain rule. This one, dA dt, would equal 8 pi times r dr dt. Okay. Now we've got a couple equations where some of our things work. And, I suppose you could try to start putting an r in here and r over here and trying to figure out some relationship between dv dt, dr dt, and dA dt. But at this point, I would like to encourage us to recognize that the expression for dv dt and the expression for dA dt are pretty similar. And honestly, if I wanted to, make one look almost exactly like the other, I would need to pull a factor of r out over here, and I would need to actually divide by 2. So if I pulled out a 1/2 r from this part, notice how, this whole section is the same as dA dt. And in order to make a, an equation that relates dV dt and dA dt, we could actually just make that substitution now. And what that gives us is an equation that relates dV dt, dA dt, and the radius. Notice that by doing it this way, we never actually even needed to figure out the rate at which the radius was changing. That dr dt kind of just faded away as we did the substitution. And that's convenient because we didn't have a number for that. We can work with what we got now, and dV dt is 200 cubic centimeters per second, or per, okay. And we've got 1/2 times the radius, which is 20. So if we solve for dA dt here, we would have 20 is equal to dA dt. And that's 20 square centimeters per second. Cool. All right, and so I guess, I made the substitution after we had taken the derivative. I guess one of the things that I just thought this time going through the problem was, what if we made a substitution and tried to relate these two before even taking any derivatives? Let's test it out real quick and see if that works. So if I wanted to make, V look like A, I could zoom in there and I could rewrite this as 4 pi r squared, but that would leave a 1/3 and an r hanging out over there. So if I wanted to try to do this, I could say V is equal to 1/3 r times the surface area. Okay. And if I take the derivative with respect to t on both sides, we're gonna get a product rule on the right-hand side. Let's see what happens. I'm still curious. Honestly, I've never done it this way. So if this is a horrible failure, I'm sorry, but part of mathematics is exploring. And so it should be cool. Let's see what happens. Okay, so chain rule. Let's view this as F, or not chain rule, product rule, sorry. Let's view that as F and G, and let's do the product rule down here. So derivative of the first part, and let's go ahead and, I don't know, I'll even put these in parentheses to separate them out a little bit, just so that we know that the 1/3's hanging out with R. If we take the derivative of that with respect to t, we would have 1/3 dr dt plus, or times A, plus goodness, just write down the first part and then multiply that times dA dt. I'm sorry if this is a little small. Notice as we've done the product rule here, it looks like we've got an a in there that I'd kind of rather not have if possible. Although, we can rewrite that in terms of 4 pi and r squared. So, you know what? Let's keep going. We're not out yet. 1/3 dr dt times 4 pi r squared plus 1/3 r times dA dt. All right, and that's oh, on this one we actually do need to know dr dt. Woof. And so, I mean, yeah, all right. We could keep going. You could find an expression for dr dt in terms of dA dt by taking the derivative of both sides with respect to this and, getting this and making a substitution in for dr dt in terms of, it's dA dt divided by 8 pi times r. Ugh. But obviously, okay, the first way that I showed you worked out to be nicer. The new exploration, while it would be possible, it's just not working out as nicely. Lots of steps. But we did get to see a product rule, so it wasn't a worthless exploration. Okay. I'm gonna move on to the next one. If you guys want to finish that, you can, but you'd be substituting that in, and yeah. Anyways, let's keep going. On to section 3.9. We're gonna look at linearization and differentials. Actually, we've done a pretty decent job of looking at this already, especially, inputting tangent lines that can move into GeoGebra is something that I've tried to, push us towards ever since we started looking at derivatives, even when we were doing the limit definition of the derivative. Yeah, if we have a function f and it's differentiable at the point c f of c, this is an equation for the tangent line. And you multiply the derivative times the quantity x minus c, and you add the y value, which is f of c. So yeah, tangent line, cool. Also can be referred to as a first order approximation because a line is a first order polynomial. Yeah, actually there will be higher order approximations later on. Towards the end of Calculus 2, we will look at Taylor series, which is really cool. Example number 1. Find the linearization of f of x at x equals 0. In this case, don't worry too much about this because a linearization is just the equation of the tangent line. And honestly, I copied this picture in and the equation's already there. But I think it would be good for us to actually figure this out. So yeah, we're finding the equation of a tangent line. And in order to do that, we would need to take a derivative. The derivative, we would be using a chain rule because we've got a composition of functions here. Derivative of the outside is 1 over 2 times the square root of everything on the inside times the derivative of what's on the inside, and the derivative of what's on the inside is just 1 because it's 1 plus x. The coefficient on x is the only thing that survives. And that's the derivative. And so, yeah, the linearization would be the derivative evaluated at a point times x minus c plus the y value, which is just f of c. And so in this case, our c value is 0. So f prime of 0, x minus 0 plus f of c, or so f of 0. And then we just go through and evaluate all these things. We put a 0 in here and we get 2 times the square root of 1, which is just 2. So the derivative is 1/2. This part is just x, and then plus f of 0. When we put in 0, we get the square root of 1, which is just 1. So 1/2 x plus 1 is the same thing as the linearization that they found before. That part, we've been doing it. I don't know. I guess I haven't. Most of the time, I've just shown you a linearization that I've already done. Let's go ahead real quick. Sorry if this is super boring, but for the sake of completeness, let's, no, that's not what I wanted. Open up this great algebra. Let's make it real quick. Come on. And we can see the slidey tangent line. I guess it's, I hope that's not getting too old for you guys. All right, our function is square root of 1 plus x. Boom. We could even put a c in here. I guess I should have made it equal 0. Normally I just type in 1 to make a slider. Cool. What we can do is make a point on that function, and I would do that by making c comma f of c. And yeah, I guess since the domain of this will be -1 onward, maybe we can zoom in a little bit, and then yeah, we can see this point just cruise along. I don't know, let's make it blue and bigger. Okay. Yeah, that's cruising. If we want to make a tangent line that follows that point, yeah, honestly, GeoGebra is smart enough to be able to write f prime and know that you want to take a derivative. So it is really just as easy as saying that we're going to make a new function. We're calling it L of x. And then we're going to do f prime evaluated at c times x minus c plus f of c, the y value. Whoopsie. But yeah, there's our slidey tangent line. And when c becomes 0, we get 1/2 x plus 1. That's gross. 1/2 x plus 1. All right. Cool. Back to OneNote. All right. Yeah, and just to give you a little bit of a sense, like linearization, this process of finding a tangent line, actually be really nice, because the closer that you zoom in on a function, wow, that again teleported me. The closer that you zoom into a function, the more that it starts to look like a line. And so for local approximations, using linear functions is actually really useful. And so, and there are lots of tools that mathematicians have developed to, analyze linear functions and make use of them. We're going to learn all about them in linear algebra. If you take linear algebra with me, not this coming spring, but the next one. probably. But yeah, it's really nice to have tangent lines because they're simpler functions than, just a general derivative function kind of, yeah. It's nice to work with lines. Example number 2, good grief. Secant squared did not get erased. All right, here we go. Example 2 is just finding the linearizations of sine, cosine, and tangent at z equals 0. And yeah. You know what? I think we're just going to do tangent because sine is pretty obviously y equals x for that line. Cosine is going to have a flat slope and it's going to be up here. So, tangent line, or sorry, well, yeah, it is a tangent line. The tangent line of cosine at theta equals 0 would just be the line y equals 0. Yeah, and this line's y equals theta, I guess. This is the theta axis. But yeah, that just has a slope of 1. But I think it would be a little bit more interesting to do all the steps on tangent. So if we want to find the linearization of tangent, we'd need to find the derivative. So if we take the derivative of tangent with respect to theta, we would get secant squared theta, and yeah, when we find secant squared of 0, that's just going to be 1 because secant is 1 over the cosine, and cosine is 1 when theta equals 0. So, I mean, maybe this wasn't super exciting. Here we're finding, I don't know, maybe we call this f prime of theta if tangent is equal to f of theta. And this one is f prime of 0. So if we want to write out the linearization, and I guess it's in terms of theta now because theta is acting as our x-axis, we would, have the slope 1 times theta minus our c value, which in this case is 0, plus the y value. So if we put in 0 in for tangent, yeah, the tangent is 0. So I guess this is really boring again, but the tangent line again would be y equals theta. It would be the same as the sine. And that makes sense. Yeah, if we hide all this stuff and put in a tangent, yeah, having a tangent line of y equals x makes sense. Cool. But that was just a little bit more practice using thetas instead of x, so it takes us out of our comfort zone a little bit. Okay. Moving on to differentials. Again, differentials are not completely new to us. We've treated these differentials as tiny little nudges. And we've evaluated limits where we were looking as dx or delta x was approaching 0. So yeah, these differentials are nudges, and dx is our input nudge. So yeah, when we nudge x, dx, then we get an output nudge. Y gets nudged in response. And the actual way that these differentials are defined in our book is by this equation, and the derivative, shows up here as the rate between a nudge in x and a nudge in y. So the rate at which a nudge in x affects a nudge in y. And yeah, just to remind you, we've looked at this very, very recently. If we go back here, yeah, when we were doing the chain rule, we were actually doing multiples of this. But when you're moving from, the x input to your intermediate variable to your final independent variable, we nudged x a little bit, and that created a corresponding nudge in the function g, and it was this rate between the two nudges was dggx. So we've seen these before. Yeah, and the derivative is the rate at which those nudges correspond. Here we've got a nice picture with lots of things that are labeled. What's important to point out? Well, our tangent line makes an appearance here again. Notice that dy is the change in y values along that tangent line, whereas the delta y that we've worked with in the past, that's more along if you wanted to create like a secant line here. Yeah, between these 2 points, delta y and delta x would be relevant to the secant line that goes through both of those points in the function. And the stuff that we've looked at before, the derivative gives us a relationship between all of these things, that the limit of the ratio of secant lines, the slope of secant lines approaches the slope of the tangent line as delta x goes to 0. So that's just some context for these differentials. Yeah, but dy is moving along the tangent line at some point c, because that's the way that dy is defined. It's the slope times the nudge in x. Okay. We got example 3, and that one's gonna be, we're almost done. Example 3 with huge letters. Determine the requested values of the differentials. And here, again, this is something that you guys probably could do just on your own right now. You could take the derivative of this function and then solve for dy, and you probably would do just fine. So if you wanted to pause and try that, go for it. What I'm going to write down here is a little bit more differentially way of notating things. But yeah, I think that you guys could do this even without talking about differentials too much. All right, so I'm just going to write down the function that we had. And in order to get some differentials appearing, I'm going to take the derivative of both sides. And yeah, this time I'm going to just write it in differential notation so that y becomes like a nudge to y. Over here, we would take the derivative of 3x to the 4/3 power. We're multiplying that by 4/3, so that becomes 4x to the 1/3 power times a nudge in x. And the derivative of the natural log of x is 1 over x. And that's times a nudge in x as well. So yeah, I mean, that's just the addition rule. We took those derivatives independently and found them here. And so yeah, at this stage, you could just plug everything in and get an answer. 4 times 8 to the 1/3 times 1/10 plus 1/8 times 1/10. 4 times 8 to the 3rd. 8 to the 3rd is 2, so that's 8. So we've got 8/10 plus 1 over 80. Common denominator, 64 over 80 plus 1 over 80 is 65 over 80. Which are both divisible by 5. And you get 13 over 16. Good grief. All right, sorry, that's moving off the page. Okay. Yeah. So that's it done that way. I mean, normally the way that we would notate this is y over dx equals the right-hand side, but the dx's wouldn't be over here. So it's kind of like we've just taken the derivative and multiplied through by dx. It's just a different way to notate it. And sometimes it might have advantages depending on what you're trying to find. Here, we're just trying to find how much y has been nudged when we are at x equals 8 and we nudge x by 1/10. For the next one, part B, we're finding what is the nudge to sine of theta if theta is 0, and we'd nudge theta by 0.05. The nudge to sine of theta will equal the cosine of theta times the nudge of theta. Again, we're working with this formula right here. It's the derivative that gives us the relationship between dy and dx. So here we've got the derivative of sine of x, mediating this relationship between the input variable and the output. So yeah, here again, we just multiply. So if we're, we could, say the cosine of theta is equal to the cosine of 0, which is 1, and d theta is 0.05. So 0.05 would just be our answer there, the nudge to the y value. Cool. Example number 3, almost done. All right, example number 4 again, is playing with inputs and outputs. Here we have the radius of a ball bearing. It's measured by micrometer to be 1.2 millimeters with a margin of error of 5/100ths of a millimeter. Given this possible error, estimate the maximum error in the calculated volume of the ball bearing. And I chose just to leave the solution here and we could talk through it. But yeah, since we're looking at the error in the calculated volume, we use the volume formula. We could take the derivative of both sides. Here we're taking the derivative, using the differential notation. Normally, if we were taking the derivative with respect to r, this would look like dv dr on the left-hand side, and it'd just be equal to 4 pi r squared. Here we've got those differentials split up. And yeah, we can find the nudge in the output volume. And that's just 4 times pi times the radius squared times the nudge to the radius, which is the error. And we would see that the volume has been nudged by about 0.9 cubic millimeters. And to get some perspective on this, these are what we would call absolute numbers, the 0.05 millimeters or the 0.9 cubic millimeters. But it's sometimes nice to know the percentage error, so that, based on the scale, we have an idea of just about how much error is possibly there. In order to find the percent error, you just take the actual error and divide it by the length of what you're trying to measure. So here we're finding the error in the radius. And so that's about a 4% error. And notice that when we get to the volume and we compare the nudge to the volume and the actual volume, we get 2% instead of 4%. And that growth in the propagated error always happens when you are comparing linear values to cubic values or volume values. So that's cool. It's not a coincidence that one of those is 3 times the other. You got to imagine that when you're making a nudge to an input like that, like the radius of a sphere, that nudge to the radius kind of gets calculated 3 times when you are, working through this volume formula. So the fact that those absolute percentages are related by the number 3 is not super surprising. Cool. All right, well, that's it for today. I'll see you tomorrow. Bye.